I think bioengineering is a relatively non-term in the society, but immunoengineering is still something that holds novelty. So, can you please explain what it is about?
Sure. Yeah. So immunoengineering actually is a branch of bioengineering. And if I might put it loosely, it is a way of using engineering principles or bioengineering principles to modulate your immune system or to manipulate your immune system to fight a particular disease or infection. Or it could also be methods that you could use to create models of diseases that affect immune pathologies or have an immune connection where you're studying the disease along with the immune cells in that context. So that broadly is immunoengineering. So it could be, for example, the use of nano materials to modulate immune cells, or it could be that's typically how it is used. It could be areas where you could use it along with a vaccine or as a therapeutic, or you could use materials like hydrogels to create models of immune niches. Yeah. So this is what broadly immunoengineering is.
That sounds very interesting, and it's like an amalgamation of biology and engineering. So, coming back to your PhD journey, given your engineering background, we'd actually love to know more about your PhD journey and like what was your research like about how did you find your way into this field?
Sure. So my PhD thesis broadly looks at using these bioengineering strategies to either model immune cells or to modulate them. Essentially, it didn't. I mean, I'm actually an accidental immunoengineer in the sense I didn't come into this field by choice, thinking when I started my PhD that I would end up becoming an immunologist slash a bioengineer with an area of expertise in immunology. But what happened was I started out as a person who wanted to do a lot of work in the area of neurodegeneration and looking at using imaging tools like microscopy and using molecular biology tools and combining them to understand how organelles play a role in neurodegeneration, such as mitochondria and their interactions with microtubules. But during the pandemic, in the course of that time, I had to switch labs because of certain circumstances, and then so when I changed my labs, I looked at some PIs that I could work with, and so the area that we together came up with was immunoengineering, because I was working together with an immunology advisor and an advisor who had expertise in materials engineering and biomaterials. So that's how it came about. So initially we worked on looking at using materials like nanoparticles and seeing what effects they have on immune cells, whether they make it more more pro-inflammatory or shift them more towards anti-inflammatory phenotype, in the sense whether they excite the immune cells more and make them more activated to fight off the disease, or do they suppress the immune system. So that's broadly something that I started looking at. And eventually we also had the tools to create disease models in vitro using hydrogels and using bioprinting technology. So I sort of combined these areas and we then looked finally at using biomaterials to either model immune niches like bioprinting T cells, activating them in the bioprinted hydrogels, and then seeing how they differ from the conventional 2D cultures, and also looking at how T cells get activated and how this, apart from this physical microenvironment that you create in 3D using these bioprinted hydrogels, how are the biochemical signals playing a role in the sense, if you increase calcium levels, for example, inside in the T cells while you are activating them, If you increase them beyond a certain point, how do the T cells respond, or do they get activated? Do they get inhibited? So these were broadly areas that I looked at, and finally we used a 2D nanomaterial that could modulate the immune cells a certain way to alleviate an autoimmune colitis model in mice. So this was broadly what my PhD consisted of, and in between, I went to the US on a Fulbright fellowship, during which time I also did a short work there, which also looked at using hydrogels to create these 3D niches of different stiffnesses, and how the stiffness plus the cancer secretome would have an effect on T cell subpopulations. This was something that I studied while I was there.
It all sounds very complicated, but I would just like to ask a very basic question. Like, what exactly is, like, can you clarify what exactly does a hydrogel consist of, and like, what
Right.
does it do?
So, yeah. So, I'll try to break it down a little bit. So, hydrogels are materials that can, I mean, many of these hydrogels sort of mimic the kind of environment that you have in the tissue spaces in the body. So, I mean, we all know of gelatin, which we use in ice creams, right? So, that is something that we used basically as the mesh in which the cells are present. Because in the body, you don't find cells just floating around, except for cells that float in blood or the lymph node or the lymph. These are, of course, cells that are floating in the body. But apart from that, in most of our body tissues, they are actually present along with an extracellular matrix. So the extracellular matrix consists of many proteins like collagen, fibronectin, hyaluronic acid, which is a carbohydrate, of course. So these are extracellular matrix proteins that actually are holding these cells in an organized way in the tissue. So that's something that we are trying to mimic outside of the body. So when you do that, you actually need an extracellular matrix component and the cells present inside that extracellular matrix component. So what we do when we bioprint T cells is we use gelatin, and we mix them together with T cells, and we use a few other components so that there is the cross-linking of the gel, or that gel is particularly formed. So you could use different techniques. We used a light-based technique. So we used a photo cross-linker and a photo initiator, and a photo absorber that would basically hold this gel together by a chemical reaction. So what we do is, so then when you do bioprinting, what happens is you actually print these cells in a layer by layer fashion. So it's basically a more advanced form of 3D printing. I wouldn't say advanced form, but something that involves cells, which is why we call it bioprinting. So it's kind of 3D printing where you print like layer by layer. So you have cells that are formed. So you create a model using a software of a particular shape that you want to print the cells in. And so you have this cells within the gel that then goes on printing layer by layer. So if you are printing a flat sheet, you can print, let's say, a 1 mm height of a flat sheet containing of this gelatin containing cells in it, where you will print it in a layer, in like, let's say, 10 layers of 100 microns, right? So I mean 10 microns each, which will add up to 1 mm, right? So that's something that we're doing. Yeah.
That all sounds very advanced. So, speaking of these advanced systems, it shows that there has been very rapid development in the biotechnology as well as healthcare space.